Okay, all right. So, hello everyone. My name is Paolo Galeone, and today I will talk to you about this custom model training and deployment on Google Cloud using Vertex AI in Go. So, in practice, I will show you how to deploy not only a trained model, but the whole machine learning pipeline. So, to begin with, just a brief introduction. So I am a computer engineer with a master's degree at the University of Bologna. I am the technical lead of a company named Zurtec. I am a book author as well, so I wrote in the past, so it has been 2 years, more or less, that I wrote that book on TensorFlow 2.0 at the beginning. And I am also a blogger, so I write my articles that are pretty technical stuff on this pgaleone.eu. I write a tons of software, and in practice I focus my free time on writing open source software, mainly using Go, TensorFlow, machine learning stuff, C++, and other languages. And I'm also a fan of Rust. I'm also a GDE, that is the Google Developer Expert. That is a status given by Google to people that are expert in their technologies. And in my case, it's about TensorFlow. So let's go straight to the point of today's topic. So to begin with, I want to show you this simplified machine learning workflow. So that is a very schematic way to represent what happens in practice when you are going to train and deploy a model. So you need to get the data, clean the data, train the model. Of course, you need to define it, understand your data and stuff. Then doing the model selection, and then deploy it. Of course, usually, unless you are pretty crazy, you use strange technologies. The great majority of the work is executed in Python. So the data cleaning, the model training, the model selection, and perhaps even the deploy, it's executed in Python. Of course, depending on your target deployment, the technology may change. So for instance, if you are targeting an embedded device, of course, perhaps you cannot use Python, but you have to use something else, like deploying using C libraries. Or if you are using or developing on a web server, you need to deploy on the cloud. But this pipeline only works if we have multiple users that can use the same model. But what if the data cannot be shared among different users? For instance, in the domain of healthcare, it is prohibited by the law to mix data from a patient and another. So my data must be only about me. I cannot use it. I cannot even send it outside of a particular domain. So in this case, we have several users, and for each of them, we need to train and deploy a model. Of course, we can do it manually, but this is going to be pretty boring and, of course, a very repetitive stuff. And in practice, we need a platform that helps us in doing all of this at scale. Because, of course, if you are developing an application that is going to be used with a personalized model by hundreds of users, we need something that helps us in doing it. Of course, there is a platform for this, and it's pretty trivial because, of course, it's a cloud. The cloud is just someone else that manages the servers for you. So we need, of course, to have the support for handling a huge amount of data, because depending on the data, on the problem that we are solving, perhaps it may happen that we need to handle petabytes of data. We need to transform and load the data at scale, and of course, we need all the support for training and deploying the model. So let's go straight to the reality. So in practice, the task that I'm going to present, that is an example, but it's gathered from a real-life scenario, it's to develop a solution that is tailored on the user, and the goal is to predict the sleep quality. So for instance, I'm wearing this is a Fitbit device, And this device it's right now producing a lot of data. It's constantly monitoring my heart rate, my heartbeat, everything in practice. Of course, there are also an associated application where I can log my physical activities, what I eat, and in practice everything about myself, my activities, and what I'm eating, and these kind of things. So the goal is to use this data to predict, given the activities and what everything else I've done during the day, how I will sleep, if I go to sleep well or not. This is highly subjective. For instance, I am a marathoner and I can easily run and then sleep well, but perhaps other people cannot sleep well after running 20 kilometers. So we need to end up in the exact scenario in which we need the model for each user, because of course different people have different habits and respond differently on their activities during the day. So we're going to doing it using Go, but it's just because I like the syntax. In practice, as we'll see, it's kind of trivial. It's just using an API. But before doing this in Go, we needed to work in Python and Docker, because of course, for interfacing with the cloud, we needed to work also with Python and Docker. So, of course, as I was mentioning, cloud is the right environment for these kind of problems, because it scales. So if we have one user or we have 100 users, it doesn't matter. Of course, we need to pay. And the cloud, of course, provides a model deployment platform. It provides a platform for training models, and it provides, more importantly, a deployment platform. And the idea is to use the cloud, but not manually, but using a programming language. Therefore, we can write an application that interacts with the cloud, and every time a user submits new data, it just defines, gather all the data, execute the machine learning workflow shown previously, and then deploys the trained model. So the decision of using Go, of course, is because I like the syntax. It's pretty challenging because it's not widely used, and the ecosystem for deploying a web application is kind of rich. Anyway, the language can be any language, because what it really matters is to have a client for the cloud that we're going to use. And in detail, we are going to use the Google Cloud Vertex AI platform, and therefore any language that has a client for Vertex AI, it's suitable. So Vertex AI, exactly, it's the Google solution for having a managed ML platform. So in practice, it's a toolbox that every practitioner can use in order to train, deploy, and develop machine learning applications. There are a lot of things possible to do in Vertex AI. Of course, all of them have a cost. So if you have to experiment, be careful about the pricing. But of course, it's really a great thing, because of course you can just allocate different hardware devices, you can just decide everything, and you have the full control of what's happening on the cloud. So focusing into the tasks, of course we are solving a task and we need to have some data. This device, the Fitbit, produces data on a tabular Yes, it produces tabular data in practice, so we have a table-like content. So for instance, this is an aggregate, an example. So we have these calories during the day, the number of steps, the average heart rate, the calories, the distance performed in kilometers, and so on. And our goal is to predict the sleep efficiency. The sleep efficiency is just a number between 0 and 100. Of course, we need to have this data and working on the cloud. But working on the cloud means to have the data stored on the cloud. And in practice, the way of storing files is to use cloud storage that can be or a cloud database or cloud buckets. In this case, we are going to use cloud buckets. So the first step is to create a Google Cloud project. This is perhaps the only steps that is manual. So we are going to create the project from the Google Workspace, and you need to sign up and then create the project. And you will end up with a service account key that is an identifier for your account and a project ID that is the ID for your project. We are going to set this, the path of the service account and the project ID as an environment variable in order to access them from our Go application. Then, since our goal is to predict the sleep efficiency, one of the possible ways that works pretty well is to use a plain old decision forest. So even simpler, a single decision tree, it's enough. So a decision tree is a typical machine learning model that has the great advantage of being interpretable. So the training means to just learn the condition. In practice, what we are going to do is to just give to a library that's named TensorFlow Decision Forest our old dataset, and we let the TensorFlow Decision Model learn the various conditions in order to go from the root to the leaf. And of course, our leaf will be the 100 possible outcomes of the sleep efficiency. So we are going to treat, even if it's a numerical value, we're going to treat it as a classification problem, because after all, 100 values are pretty low number. So we have decided to use a TensorFlow Decision Forest and to train a simple decision tree. But for doing it, we have to do a lot of things, because this is the problem of working with the cloud. You need to stick with the cloud limitation. So TensorFlow, it's an official TensorFlow product, but TensorFlow Decision Forest is an official TensorFlow product, but it's not supported natively by Vertex AI. Therefore, we need to follow this pipeline. We need to write our Docker file where we are going to install TensorFlow Decision Forest, where we are going to install all the required dependencies. Then we have to define our training script. And the thing is, when working with the cloud, you have to be a good software engineer. You have to write clear API for your application, because of course there will be some other services that is going to use your application, in particular for training the model in this case. Then we have to push the model on the container registry and then start the training. The thing is, with TensorFlow, even with TensorFlow Decision Forest, we have this common format that it's the saved model. So once we train the model, we can produce a saved model, and then with this saved model, we can go on any deployment platform. In this case, we're going to the cloud, and we just need the training model to load it and run inference. So, as I said, you have to be a software engineer, and therefore we are going to define our Python training script in order to have a clear API. The clear API, in this case, requires, of course, a description of the training script and then some parameters. One is the data location, so is the full path over the Google Cloud Platform, so on the part where we store the data on the cloud. And then it's the model destination. There will be, once again, a path over a bucket where our trained model will be put on. Then, since this is a decision tree and potentially we can try to predict every single missing attribute, we are going to specify from the outside the label, so the attribute that we want to predict. So this is our train.py script, and we are going to first parse the arguments. Then from the outside, we can fetch some environment variables that we are going to set from our Go application later on. So for instance, in this case, the Cloud ML project ID will be injected from the outside. We need this Cloud ML project ID variable because when we are interacting with the storage, when we are interacting with any part of the cloud, we need to be authenticated and we need to have all the variables correctly set. Then we use the Google Cloud Storage packet in order to list all the possible buckets, and then we are going to search if the bucket specified by the command line exists. the thing is, even if we are writing Python code, we have to write cloud-native Python code, because we cannot just open a file and write the file. We need to use the cloud file system. For instance, in this case, as you can see, there is no the classical open file in the read, but there is the blob, that is the bucket, pointed object file on the bucket, open. So even the Python code they are going to write must be cloud native. Then we are going to train the model. Luckily, with TensorFlow Decision Forest, training the model it's trivial. So we just import the TensorFlow Decision Forest package. Then, of course, we are going to do some data preprocessing, some split. We are going to remove the labels that are not correct. We are going to filter if the label passed by the CLI is the right one. We're going to drop possible useless data. And as you can see in the last line, with a single line of code, we can go from a pandas data frame. So we have read earlier the data stored on the cloud in a CSV format as a pandas data frame. And then this pandas data frame can be converted to a TF data dataset in a single line of code. The TF data dataset is the optimized way of feeding data to any TensorFlow model. Then, thanks to the beauty of TensorFlow Decision Forest, we can just define and train the model in 2 lines. So here in tfdf.keras, we are importing the CART model. This is the classification and regression tree model. And then we just fit this model on the data. That's it. Then we are going to save locally, so in a local path, this trained model in a folder trained model. But then we have to, once again, write cloud-native code. Of course, there is no way to save this created folder on the cloud as it is, but we need to write this boilerplate code down here in order to simulate the folders. Because, of course, in the cloud, at least in the Google Cloud bucket, we don't have the concept of folders, and we need to write explicitly every single path. Even the writing of the files, it doesn't look like a traditional Python code where you need to upload from file name and use the cloud API stuff. Then we have reached the end of the training script, and we have to write our Docker file. The Docker file, of course, it's a way to create a Docker image that is an isolated container that executes the code that we are writing inside. So we inherit from the official TensorFlow image, we install our requirements, and then we say that when you are going to create a container for this image, the first thing you're going to execute is Python with the train.py script that we copied inside the container itself. There are several limitations when working with the cloud. We have to specify the name of the image that you are going to upload must match a specific syntax that is well documented, at least. And potentially, we can also use this model locally. But anyway, we are going to authorize, so we are going to log in to the Google Cloud storage for our containers. Then we are going to build the container, and we are going to push it on the repository. Then, once we have the support of the Docker images, we can start creating the client. So creating the client is trivial. So every time we need to follow the very same pattern. The thing is, there are multiple clients for multiple actions that are possible to execute on the cloud, and we need to just pick the correct client, create and populate the request, because in practice the client is just a wrapper of our REST API. So we create the client, populate the request, use the client to execute the request, and wait for the completion. So this is the first bunch of Go code. So we have this example that it's a way that we are going to use to upload the custom user data over a bucket. So we use the storage package. We create the new client, so the storage client. And then we are going to upload on the bucket the custom data for the user. Of course, for doing it, we are going to get the data. So there is this all user data that is a function that fetches the data from the feedback API that is not shown here. But the thing is, you fetch the data from somewhere, and then you have to upload it. Then you have to use this bucket object in order to upload it to the cloud. Of course, there is always the same pattern. Then we are populating the request, using the client, wait for the request to complete. And in this way, we have uploaded the data. Then we have to ask the cloud to create a training job. So we have to use the job client, that is the client that is able to communicate with Vertex AI to ask for the creation of training jobs. Then we have to create and populate the request. This is perhaps the most strange part of the whole talk, because the create custom job request, it's pretty much like a huge JSON that needs to be filled. And we have to specify all these fields. All these fields, of course, have a meaning. For instance, the destination is the destination where the trained model will be uploaded on. And then, since this is a training job, we have to specify the hardware that our training application will use. The hardware, of course, will fetch our previously uploaded images. So the image URI points to the image of the Docker image that we previously uploaded on the cloud. And the args are the arguments of our train.py script, where we specify the buckets. Then, from Go, we can set inside the cloud container the environment variable. So we can specify the variable needed by the train.py script. So in this case, the cloud ML project ID. Then we can set the hardware. So there are these machine spec that are the specification of the training machine. These machine types have a huge list on the Google Cloud documentation. In this case, we have just a single stupid standard machine with few RAM and no accelerators. But for instance, if you're going to train a model on images, audio, or whatever, you can specify the type of the accelerator, so you can choose to use a CPU, a TPU, or whatever, and you can choose how many of these has to be visible to your training script. Of course, we also specify the specification for the disks and potentially all other the fields that describe the hardware needed. Then, once we have fulfilled the request, we have to use the client to execute the request. So this is trivial, and in practice, we are just sending this request, and we are waiting for the completion. So waiting for the completion in this case is quite a bunch of boilerplate code, even in this case, because this job, it can take time. Of course, it's the whole training that it's going to be executed right now when we hit this line. So we have to just poll constantly the server in order to understand if the job is completed or not. So this is the outcome. So we can go in the Vertex AI, in the custom job section, and we see that our sleep efficiency model has been trained. So the custom job executed correctly, lasted 30 seconds in this case. But unfortunately, this is the cloud, and the cloud is quite boring to work on. So we cannot use it. But we need still to upload the trained model on the Vertex AI model registry, and then we have to expose this model to the public. So the thing is, we need to upload the model to the registry, and once again, we have the model client with this other RPC call that is upload model, where we're going to specify the model name, and in particular, the important part is the container spec. So the trained model, it's a saved model. This saved model can be executed in a certain runtime. There is no need to use our custom image because the saved model only needs the TensorFlow runtime to be executed. Therefore, we use in this image URI, we specify the default TensorFlow to CPU image. Then this is the way for uploading the model and specify the execution runtime. And after that, we have uploaded the model on the model registry. So right now, we have the model uploaded there, and it's deployed, more or less, because in practice, the model is there, but there is no way to get in touch, to connect to this model. We have to really deploy it. So we have to create this endpoint. The endpoint in practice is we have to spawn a server. This server needs to expose a REST API where you can make requests by sending your data and waiting for the model prediction and getting the result. The way for creating the endpoint is once again following the same pattern. So you create this endpoint client, you fill the data. So you are going to telling that, okay, this is the endpoint, that this is the endpoint name previously deployed. And we are going to deploy the endpoint there. So sadly, this is only the endpoint without the association with the model. So we need to create the association between the model and the endpoint. For doing it, we need once again to specify the hardware. So we need to create a resource pool where the model will be executed on. So we're going to create this resource pool that is just a bunch of hardware available on the cloud. And we say, once again, that you need this simple N1 standard 4 machine with no accelerator, with no replication. And this is the specification of the hardware. We are just to define the hardware to use. And then, finally, we can create the association between the endpoint previously created, the hardware that needs to be used, and finally reaching the real deployment of the model. As usual, following the same pattern. So we have to create, populate the request, and wait for the request for the complete. And then we have the final result. The final result is that we have really a deployed endpoint that is an association between the trained model and the hardware to use. And in practice, this means that we have an URI, something that we can use to make authenticated requests. So this is the very end. In practice, what we can do now is that we have this endpoint, so the HTTPS, Europe, and stuff. That is the endpoint generated by all the Go code. We need to authorize the request, so we use this gcloud out print access token in order to make authorize the request. And we have to specify the input data. The input data, it's an array of instances where we are going to pass all the data gathered by, for instance, a single day of data gathered from the Fitbit. Then we execute the request, and we get as return the array of predictions. The array of predictions, it's just the 100 values, where we can run the argmax over the array in order to get the position of the highest point. That means that the score of our sleep efficiency will be that one in that position. For instance, in this case, it will be, I guess, something like 74. Of course, when we make the request, we also have some meta information in the response. So we have the information that this is the first model deployment. So we have the model version ID. The cloud allows you to have multiple versions of the model. You can go back and forth in order to evaluate changes to the model and understand if there is data drift or these kind of things, and other meta informations. So to conclude, this is the takeaways. So you need to, in order to have a really train and deploy on the cloud, and so be able to design some scalable machine learning pipeline, you have to train and export the model, upload the model to the cloud storage, create the model in the model registry, upload it, create all the stuff needed, create the endpoint, but the endpoint is just a path, then create the association between the deployment resources, so the hardware to use, and the trained model. In the very end, the thing is, interacting with Vertex AI follows always the same pattern. It's just a matter of picking the right client, fulfilling the request correctly, and waiting for the response. So that's it. Thank you very much.